Hello everyone, welcome back to our course, Network Analysis and Transmission Lines. Today's lecture is about the transient analysis of RLC circuits having DC excitation. So in the previous classes, we have seen the transient response of RL and RC circuits. So here we are going to look into the analysis of RLC circuits, so where the resistor, inductor and the capacitor are connected in series with the DC source, right? So these are the outcomes of our presentation. Transient response of series RLC circuit having DC excitation. So in this, by the end of this lecture, you are going to derive the expression for the current expression for the transient response of RLC circuit, and you are going to estimate the damping conditions, that is the overdamping conditions, underdamping conditions and the critical damping conditions. So let us consider a series RLC circuit as shown in this figure. So you can see here where the resistor R, inductor L and the capacitance C are connected in a series to a voltage source, DC voltage source, using a switch S. Let us say this switch as S, right? Let us say this condition is closed at t is equal to 0. So now, estimating these initial conditions, we are going to derive the expression for the transient current. So here, so previously in the RL circuit and RC circuit, so we are having a single energy storage element. So that is the reason why we have solved the RL and RC circuit using the first order linear differential equations. But whereas here we are having two energy storage elements, so that is inductor and the capacitor. So coming to the circuit point of view here, when we are having two storage elements, energy storage elements, so we can say this is nothing but the second order circuit. This is nothing but the second order circuit. So now applying the KVL to the loop, so applying the KVL here to the circuit where the current in the loop is I here. So when the switch S is closed at t is equal to 0, right? These three is going to be in series, and this inductor and the capacitor is going to charge slowly, right? So now applying this KVL to the circuit, we can see, so what is the EMF acting across the loop, which is nothing but V0 here. V0 is equal to sum of the potential differences across different elements. So what are the elements here? The resistance R, which is nothing but the potential difference across the resistance R is I into R, because the current flowing through the circuit is I. And also the potential difference across the inductor is given by L di by dt, right? And the capacitor is going to be given by 1 by C integral of I dt. So this is the expression which we got from by applying the KVL to the series RLC circuit with DC excitation, right? So now by differentiating this above equation, because to convert into the differential equation, we are having an integral in this equation. So to nullify that, we are going to differentiate this equation again. So when we are going to differentiate this equation, we can write, so we are having L d square I by dt square, which is nothing but if we differentiate L di by dt, L is the constant here. So we are going to have d square I by dt square. And similarly, we are having R into I, where R is the constant over in this term. So we are going to have R di by dt plus, and we are having integral of I. So I is going to be our derivative of your integral of I dt. So I by C, because here we are having 1 by C. So which is equal to, so derivative of this voltage is going to become 0. Right? So now which is equal to, or we can write the same expression in this form, which is nothing but, which is the popular equation in your differential equations. So which is nothing but P square. So P is nothing but the derivative. P square means second order derivative. Right? P is nothing but the first order derivative, and P square means second order derivative. And taking L as common in this equation, we are going to have, if we take L as common and we send this side, we are going to have d square I by dt square. So if I consider P is equal to di by dt, which is nothing but the first order derivative, di by dt. So I can write P square d square I by dt square as P square. So P square plus, if you take L as common in this, we are going to have R by L over here. R by L into di by dt is nothing but P plus I by C. Right? 1 by LC. If you take L as common, here also you are going to have LC. So 1 by LC overall multiplication with the term I, the current I. So we are having the expression that is nothing but P square plus R by L into P plus 1 by LC into I is equal to 0. If you closely observe this equation, we can say this is of the form of the second order homogeneous linear differential equation. Right? So where we can have seen this same type of equation in the form of d square y by dt square plus P into dy by dt plus y is equal to 0. This kind of equation you might have seen this. So now from this equation, so this is going to be the characteristic equation of this particular second order equation, second order differential equation. This is going to be our characteristic equation, which is nothing but P square plus R by L into P plus 1 by L into I. So now for this kind of characteristic equation, so what could be your solution? So I'm writing the same equation for this, the characteristic equation also for the above equation, that is nothing but the equation number 1. So which is nothing but P square plus R by L into P plus 1 by LC is equal to 0. This is going to be our characteristic equation of the equation number 1, which is our differential equation. Second order linear differential equation. Homogeneous linear differential equation. So for this, for the characteristic equation like this, what could be the roots? What could be the roots for this characteristic equation? So here the roots for the characteristic equation is going to be P1 comma P2 is equal to minus R by L plus or minus square root of R by L whole square minus 4 by LC divided by 2. So how we got this? You might have the characteristic equation in the algebra, you might have studied ax square plus bx plus c. For that, what are the roots? We can have the roots like minus b plus or minus square root of b square minus 4ac by 2a. So in this equation, what is b? R by L. So R by L is your b. So minus b minus R by L plus or minus square root of, what is b? R by L. B square minus 4 into AC. 4 into AC. What is A? What is A in this? What is A in this equation? A in this equation is 1. What is C? 1 by LC is the C. X square, if we consider this as ax square plus bx plus c, the roots can be written as minus b plus or minus square root of b square minus 4ac by 2a. So a is 1, so that's why 2 into 1 is going to be 2. So these could be the roots. right? So for this kind of differential equation, second order linear differential equation, the solution can be written as I is equal to C1 into e power P1t plus C2 into e power P2t. Because we are having two roots, so that's why we are going to have two different equations. It is a combination of two expressions, C1 e power P1t and C2 e power P2t is going to be our solution for the second order linear differential equation of the previous one, which is nothing but P square. We are having that equation, right? P square plus R by L into P plus 1 by LC into I is equal to 0. For that, this could be the solution. Where here the C1 and C2 is going to be your constants. The C1 and C2 are going to be the constants, arbitrary constants over here. Right? So now, let us solve these roots, P1, P2. What could be the roots here? We have considered minus R by L plus or minus square root of R by L whole square minus 4 by LC by 2. We got these roots. So how we will explain, how we will analyze this one? Because we are having a, if it is a plus, we can explain. If it is a minus, we can get some exact value. But it is a plus or minus. So here, as we are having a root over here, it can be a real value, it can be a imaginary value. It can be of anything. The roots can be real or it can be imaginary. So when the roots can be real, when the roots can be equal, when the roots can be imaginary, we have to consider this. So for this, let us consider, for simplification purpose, let us consider, let alpha is going to be equal to minus R by 2L. Minus R by 2L. So if we send this denominator 2 to the numerator, we can have R by 2L, minus R by 2L. So let us say, for the simplification purpose, I am considering minus R by 2L as alpha. And the beta as, if we send the same towards this one, inside the root, so we can have root over R by 2L whole square. Right? 4, if we consider it as a 4, so 2 square is going to be 4. Right? So that's why R by 2L whole square minus 1 by LC. If we send this towards the numerator side, for your convenience, I am writing one more equation for this, which is equal to minus R by 2L. If I send this minus R by 2L, if I send the normal 2 into the root, we can write root over 4 is nothing but 2. So that's why I am sending this upwards. Right. So I'm writing here 4 R by L whole square, R by L whole square minus 4 divided by LC. So in this is the whole root. This is the whole root. So if in this we can say root over 4 is nothing but 2 over here. So that's why I have sent this, right? So if we said 4L, so to write it as 2L whole square, R by 2L whole square minus 4 and 4 is going to get cancelled over here. So 1 by LC. 1 by LC. Right? So if you consider alpha for simplification purpose, alpha is equal to minus R by 2L and beta is equal to root over R by 2L whole square minus 1 by LC. We can write P1 as, we are having roots as P1 and P2. So from this we can write P1 as alpha plus beta and P2 as alpha minus beta, where the alpha and beta values are defined here. Right. So next, if we let us consider different cases, as we are having plus or minus in the equation. So what are the roots? P1 comma P2 is equal to P1 comma P2 is equal to minus R by L plus or minus square root of r by L whole square minus 4 by LC by 2. So in this, as we are here, we are having a plus or minus. Let us consider if r by L wholes 2L r square by 2L, right, is greater than 1 by LC. If it is greater than 1 by LC. So if this value, this whole value, that is, if this whole value here is greater than this whole value, so what could be the case? If this value is greater than this value, obviously here the value of this, the P1 and P2 is going to be real value, and if this value is greater than this value, here as we are having a root over, and here we are having a plus or minus value over here. So for plus, we are going to get one value. For minus, we are going to have another value. Right? So that means we are having the roots are unequal, but real. Roots are real and unequal. Right? Roots are real and unequal. So for that, if we say P1 is equal to alpha plus beta and P2 is equal to alpha minus beta, if we write by substituting the P1 and P2 values in our general solution, that is nothing but I is equal to C1 e power Pt plus C2 into e power Pt. Substituting this alpha plus beta over here, right? P is nothing but alpha plus beta, P2 is nothing but alpha minus beta. What is that alpha and beta? For simplification purpose, for just show the equation as simple, I have considered this alpha beta value. You have to write here, you have to mention here what is the value of alpha and what is the value of beta over here. So from this, we can write, we simplify this, C1 into e power alpha t, right? If we simplify this equation, e power alpha t into C1 e power beta t plus C2 into e power minus beta t. So taking e power alpha t as common over here, so we can have this equation, right? So from this, so this kind of expression, we have seen the same kind of expression in the case of series RC circuit, where we got the expression, the response as the overdamped condition. So what is this damping? So damping is going to give, so with respect to our context here, so how the voltage or the current is going to settle down, or how much time it is going to take, it is going to give the oscillations time, the time of the oscillations to take or to reach its final value or the steady state value. So how much time it is going to take? So here you can see we can have overdamping response. So it is taking more instances to settle down, right? That is why it is nothing but the overdamping condition. Current is overdamping here. To reach its final or steady state value over here, the current is taking more overdamping oscillations here. We can observe here overdamping oscillations. So that is the reason why here this condition is going to be when the roots are real and unequal, that is when r square by 2l greater than 1 by LC, we can have the roots are real and unequal and the response is overdamped condition. The response is overdamped. This point you have to observe very clearly, right? So let us move into the next case. So we are saying what r square by 2l is greater than 1 by LC. So let us consider if r square by 2l is less than 1 by LC. If it is less than 1 by LC, what's going to happen? So this time we can have the same equation. Let us consider if this value is less than 1 by LC, obviously this is going to be in the negative. So that means the overall root is going to be the imaginary. And this P1 and P2 is going to become the complex conjugate values. So what are the complex conjugate values here? The P1 is going to be alpha plus j beta. and P2 is going to be alpha minus J beta, because here we are having plus or minus. So P1 is going to be alpha plus J beta, and P2 is going to be alpha minus J beta. Because why? Because this beta value is going to be the imaginary value. This beta value is going to be the imaginary value. So in that case, substituting here, e power alpha t taking as common here, and we know that e power j beta as, if we write this equation, we can have e power I theta. We are having some formula, right? E power j theta or e power I theta, right? Cos theta plus I sin theta, and minus I theta means cos theta minus I sin theta. We are having that formulas. So if we substitute those formulas over here, and we can have directly e power alpha t, taking e power alpha t as common over here, we can have C1 cos beta t plus C2 sin of minus beta t. So you can see here the current is going to be underdamped or oscillatory. So that means here we can have the oscillatory function under damping conditions. So that means here you can see, so when it is the current is reaching to its final or steady state value, we can see the oscillations, the damping oscillations, as it is getting reduced for each and every time constant. For each and every time constant, it is getting reduced. So that is the reason why you can see this response, or with respect to the time constant, if you want to see here, so it is a under damping response. Whereas in the previous case, we can see it is a overdamped. This is a overdamped response with respect to the time constant. But whereas here we can see underdamped response. So this is nothing but the underdamped response or underdamped oscillation. Is it clear? So here why we got this e power alpha plus j beta into t? So here the solution, we know the general solution of the second order linear differential equation, which is nothing but I is equal to C1 e power pt plus C2 e power pt. Right? Where here P1 is nothing but alpha plus j beta, and P2 is nothing but alpha minus j beta. So from this, by simplification this equation, we came across this one, and from this expression we came across the underdamped oscillations. We come across underdamped oscillations. So let us look into the other case. So greater than is done, less than is done. Let us look, what if this r by 2l whole square, right, r square by 2l is equal to 1 by LC. If it is, this value is equal to 1 by LC, what's going to become? So there is no question of this plus and minus. So then obviously the roots is going to become equal. P1 is going to be equal to minus r by 2l, P2 is going to be equal to minus r by 2l. Right? So here we have to observe one thing. The roots here are going to be equal to real and equal. So when this is going to be equal, the roots and P1 and P2 is going to be real and equal, and we can say, if we say minus r by 2l as alpha here, so we can have P1 and P2 is equal to alpha. So we can have I is equal to C1 e power P1t plus C2 e power P1t. So where here we are having C1 into e power alpha t plus C2 into e power alpha t. So that means if we calculate this one, if we consider here, this t is not there over here. So the solution is going to become, the solution I is going to become e power alpha t into C1 plus C2, where this C1 and C2 is nothing but the arbitrary constants. Arbitrary constants. So this is how you are going to solve the second order linear differential equations with respect to the RLC circuits. Let us observe the response. So here you can see as it is purely depend upon this arbitrary constant C1 and C2 and is also a positive value over here, e power alpha t, it is the multiplying factor of the e power alpha t. We can observe this, the damping conditions as it is nothing but the critically damped. That means it is in between the not having either oscillations or we are not having, that means it is not taking so much of what we say, the so much of time to reach its final or steady state value. Here it is nothing but a critically damping conditions. So it is not reaching its final state value initially, or it is slowly it is reaching its final state value, but we are not having a overdamped conditions over here. We are not having a overdamped conditions. So that is the reason why it is a between that one. That is the reason why it is known as the critically damping conditions. This condition is known as the critically damping case, critically damped case. Right? Is it clear? So this is what about your series RLC circuits. So again, if we want to find the values of C1 and C2 again, so here again you have to assume the initial conditions. Again you have to assume the initial conditions. With respect to the inductor, with respect to the capacitor, you have to find the initial conditions. So assume the initial conditions, you can get the values of C1 and C2 and you can substitute the same values here and you can have the final expression. Right? But this is the general form of your transient current expressions. And same, if we get this I value, obviously the V is going to become I into R and C is going to become the voltage across the capacitor is going to become again same formula 1 by C integral of I dt, and again VL is going to become L di by dt. So substitute I over there and get the value. This is how we are going to solve the transient response or transient analysis of the series RLC circuit of the second order. Why it is second order? Because we are having two energy storage elements. Two energy storage elements, and it is also proved mathematically. It is also proved mathematically in this. So that is where if we apply the equations also, we are getting the same. We are getting the same. So that is what we have seen in the initial slide, which is nothing but I into R plus L di by dt plus 1 by C integral of I dt. So here we are having the second order differential equation. As it is equal to 0, it is a homogeneous second order linear differential equation. Right? So where the characteristic equation of this equation can be written as C square plus R by L into P plus 1 by L C is equal to 0. From this we have solved the roots. From the root we have obtained the solutions and we have estimated the different damping conditions. What are the damping conditions? Critically damped, overdamped and underdamped. Right. So this is what about your transient analysis of series RLC circuits. Thank you for listening.